All right, good afternoon, everyone. Thank you for coming, and it is my pleasure to introduce Dr. George Gordon, an associate professor in optics, photonics, and medical imaging from the University of Nottingham. He'll be giving the colloquium today, which is titled Imaging Through Optical Fibers for Hair-Thin Endo-Microscopes. So just a little bit about George. As I said, he's an associate professor and UKRI Future Leaders Fellow in the Department of Engineering at the University of Nottingham. His specific research interests include things like developing new types of optical endoscopes to improve detection of diseases such as cancer, and also including things like digital holographic imaging and displays, artificial intelligence, nano-structured optical metasurfaces, and also integrating these all into clinical studies. So clearly he has a pretty broad research portfolio. Prior to his position at the University of Nottingham, he was a postdoctoral researcher at the University of Cambridge, where he also was a mentor to me when I was doing my master's there. And so I actually remember some of the first days in the lab, I was struggling to get a laser diode to work. And he was there with me for a couple hours, got it to work, got to see the threshold current and see it perfectly linearly turn on. So George was there for me since the beginning, so it's really a pleasure to be able to introduce him today. I'm really excited to see the sort of research advancements he's been making in the last few years. So George, take it away.
Thanks, Travis. That's a very, very generous introduction. As you can see, that I'm going to talk today about imaging through optical fibers for hair-thin endoscopes. So Travis did a very good job of introducing me. So I'm first going to repeat some of that, make some factual corrections, perhaps. But I always enjoy seeing a sort of someone's story when they start a talk. So I'll give a little bit of that. Then I'll talk about the motivation and vision for this work, and including the clinical need for ultra-thin endomicroscopes. With apologies to Jennifer, who's seen a lot of this morning. And then I'll talk about imaging through optical fibers, and I'll go into a bit more detail and what that is and how we achieve that. Then after that, I'm going to talk about optical metasurfaces, which is a new thing I've been working on in the last few years, which is very much linked to the imaging through optical fibers technology. Then I'm going to talk about how we can bring those things together to try and do this advanced endomicroscopy through optical fibers, which is kind of the ultimate vision of my current work. And then I'll talk a little bit about some of the steps we're taking towards clinical translation. I sort of envision that at some point in the future this will be a useful clinical device. It's a very, very long road, but I'm trying to take some initial steps towards that. So I'll start with just a little bit about myself to repeat Travis. So some of you might have heard the name Nottingham, but I can fill in some of the details. So it's about 100 miles away from London. So it's the UK is a lot more compact than America, so things tend to be not too far away from one another. It's famous for Robin Hood and the Sheriff of Nottingham. Don't know either of these people. Population about 800,000 in the local area, including a lot of students. So there's two big universities in Nottingham, and I work at one of them, which is the University of Nottingham, and it's a bit like Arizona. It's a very sort of good research-intensive university. So there's a lot of good research that goes on there, and the university itself is got a fair number of students, and it's quite unusual in that it's got 3 campuses, including in Malaysia and China, which is the kind of an interesting experiment. So what do I do there? Well, right now I lead a team of 5 as an associate professor, and I think, as we've discussed with some of others of you that I've met today, that seems to be quite a good number for me at the moment, because I can still keep good tabs on what everyone's doing, and I can be actively involved in their projects without sort of getting too lost or being too absent. So here we all are. They were teaching me to play basketball there, which was, I think, very humiliating for me and very entertaining for them. And together we sort of have this kind of research program, which I've tried to summarize here. It's kind of centered around 3 main themes, which are optical imaging, which is kind of my main background, novel optical materials, which is something is more of a recent development, which that includes things like metasurfaces and adaptive optics, and I think the third thing, which I'm trying to expand a bit more, is the clinical translation. So bringing these things together to try and make useful clinical instruments, which I think is something that's very familiar to all of you here. So as Travis said, before I worked there, I was a postdoctoral researcher in Cambridge. And then before that, I did my PhD in optical wireless telecommunications at Cambridge. And before that, I had a brief stint as a software engineer at a company that made fruit sorting machines, which was quite different, but interesting. And then before that, I originally from New Zealand, where I did my undergraduate degree. So in addition to the sort of introductions here, I thought I might give you a bit of a sort of explanation just how I moved from those strange, quite different fields into where I am now. So I kind of started off my PhD doing wireless telecommunications. So yeah, this is a wireless router here, and I think what you will note is that the modern high-speed ones have multiple antennas on them. And the basic concept is that you can get more data if you have multiple transmitting antennas and multiple receiving antennas, because they cross-couple, and you can undo that cross-coupling in order to have effectively 3 independent data channels. And this can kind of be modeled as a kind of matrix operation between your input data and your output data. So that was kind of where I started on my PhD. But then I actually, had the opportunity to work on optical fibers. And really it transpired that optical fibers are very much the same kind of theory as this so-called multiple input, multiple output wireless communication. Because if I send a large plane wave into a multi-mode optical fiber, the light will actually propagate in a finite number of distinct modes that you can see there. And these modes are actually orthogonal. So if I pick one of those modes and I just launch that in nicely, then you just get the same mode out. So then after that, and I sort of moved into the end of my PhD and towards the start of my postdoc, I was working on building the system whereby you could actually create multiple optical communication channels by a sort of similar process to the radio frequency version, which was by using a multi-mode fiber. And you have one channel that travels in a sort of Gaussian mode down the middle, but then you have another separate channel coming from an input single mode fiber that you convert to a higher order mode, and you send that down the same fiber as well. And because they're orthogonal, you can do that simultaneously to get 2 channels. And so it was this work in using these modes of optical fiber that I came across this idea that you can use these modes in optical fibers to actually take images of samples, and these optical fibers are only 125 microns, so they've got the potential to be very, very thin endoscopes. So that's kind of how I got into that. So I'm going to come back to that in a bit more detail later on. So in this case here, I have selected modes that are orthogonal. So for example, if you have that fiber and it's perfectly fabricated and you know the refractive index profile, you can calculate a set of orthogonal modes. So yeah, you're exactly right. But if you bend that fiber, then you will get mode mixing. So I will come on to that point because you need to correct for that to get good images. So then, really, after realizing that the fibers can actually take images, then I sort of, that brings me to the motivation for this current project, which is to try and improve detection of pancreatic and ovarian cancers. So pancreatic and ovarian cancers are major killers, and part of the problem here is that they're typically detected late, as shown on those middle graphs there, and if they're detected late, then the survival rate is very poor, as shown on the right there. So the main message here is we need to detect them earlier. Part of the problem is that it's very difficult to detect these early because they're deep inside the body and they're inaccessible, and you can't really see them in enough detail using things like MRI or CT scans in order to make accurate diagnoses. So what we really need is next generation endoscopes that can access and image these. So to give some context on why that's necessary, in the case of pancreatic cancer, one route by which it sometimes is detected is people will have a pancreatic cyst that's identified by like a scan of some sort, and in order to look at it in more detail, they'll have an endoscopy and then with an ultrasound probe on the end, and they'll look for the cyst using ultrasound, and then they'll stick a needle in, guided by ultrasound, and they'll take a fluid biopsy. So this is, it's not particularly accurate. the ultrasound is not really good enough resolution to see the shape of the structure of the cyst wall, which is quite important for determining malignant cysts. Similarly, the fluid biopsy just takes fluid out, but there's not really any imaging done through that needle, which would also be useful for looking at the cellular wall structures to see whether it's malignant or not. And I'm sure many of you are familiar with the work that goes on here at Arizona about detecting ovarian cancer. And again, the need there is to make very thin probes that can go all the way through the fallopian tubes and can implement multiple modalities of imaging to accurately detect early cancer. So to make these next generation endoscopes, the two innovations that are really needed is one, to have a smaller form factor. So you want these scopes ideally to be ultra thin and also to be flexible. Then they can sort of maximize their reach around different parts of the body, and they're minimally invasive the smaller they are. And this expands the range of places and organs that you can access. The second innovation is improved image contrast. So conventionally, better endoscopes, improved contrast would be interpreted as higher resolution. So now you get 4K endoscopes, in the sort of gut where you've got quite a lot of space to move. But, there's also, you could also interpret this as having different modalities of imaging that provide better contrast for structures that you're trying to see, even if the spatial resolution is not quite as good. And it's really this thing that enables improved early detection, because we're trying to look for those subtle changes in tissue. So on that first point, the kind of existing systems are kind of chip-on-tip endoscopes, and they provide pretty high resolution, but typically they're quite big. So to get that really high resolution one, you typically get sort of a few millimeters in size. But you can buy very, very thin endoscopes off the shelf now, and they're about 0.7 mils. So that's pretty thin. But even so, those very thin ones typically only do white light imaging, which doesn't really tick the second box of multimodality imaging. So my proposed solution to this is to go back to revisit an older technology, which is using optical fibers to do this instead. So these can be typically about 125 microns in diameter, so they are substantially thinner. And the kind of main concept is that they transport light in and out of the body, so you can, in theory, have the optics needed for advanced modalities located outside the body. As I said, they've an existing technology that's been used a bit widely before, but the resolution tends to be a bit poor because of this, this kind of speckling that is overlaid over the image. But actually, this has recently changed, and it's transpired that you can actually correct for a lot of that kind of scrambling of light that goes on there. And you can do this by having total control over the phase and polarization of light. Then this is actually almost entirely reversible. And this has been a real innovation that has led us to revisit these optical fiber imaging solutions. So for that second innovation that we need for these next generation endoscopes, image contrast is key. So conventional endoscopes, they often use white light imaging modality, which is just the way your eyes see. Shining white light on tissue penetrates to different depths, excites different features, and then you just detect the light in these three wavelengths, red, green, and blue. But this isn't always good enough to detect early stage cancer. So here are some examples of white light images that are taken from a clinical endoscope in the esophagus, and these all have an early stage cancer in them. But I bet you probably can't see where they are just by looking at these images. But they're there. So what we really want instead is some kind of advanced endoscope that uses one or more modalities and provides the clinician with an overlay showing where the early stage cancer is likely to be. So I guess the kind of main vision of my work to try and achieve this is to have ultra-thin fiber endoscopes that can effectively transport advanced microscopy modalities to the end of a fiber. So you can imagine you've got these different types of microscopes here that are useful for imaging tissue, in particular cancer. And then you've got some ultra-thin optical fiber here. And what we want to do is we want to have some kind of simple optical unit on there that can take the light from those microscopes and send it down a fiber and record what is reflected back. and also that allows you to multiplex these different microscopes. So that's kind of the dream there, and if we could make that, that would be really suitable for doing imaging of early-stage cancer in places like the pancreas and ovaries. So that's the kind of vision, and I'm now going to talk a bit about what I've done towards that vision. It is a long-term vision, so I've only just started on this journey, but I'll show you what I've done so far. So the first key technology that I was working on is imaging through optical fibers. So the problem with imaging through optical fibers, and this has been the case for a while, but it's not really been, it's only been recently addressed, is that, even in a multi-core fiber like this, particularly if it's long, you send light in one point and it kind of spreads out as it propagates along the fiber. So, you get kind of like a point spread function that comes out the other end. So you might think that you can just use these fibers as a sort of, as if they're not there, like a sort of transparent optic where you can just transport an optical field, but that's not the case at all. They're actually, in a sense, very highly scattering, and so you can't really form images through them in the same way that you can with just an optic. So what you need to do is you need to characterize the fiber, really. And what this means is taking a spot or some other kind of input there and just scanning that across the fiber and measuring for each position what comes out the other end. If you can do that for the whole fiber, then you can get a full characterization of how that fiber transports light, and you can perfectly reverse that. So I now deviate from what I was showing this morning and I'm going into a bit more detail because I know this is probably more of interest to you. So I guess more formally, what we do then is we have to consider that each input as an optical field to the fiber can be represented as a vector of complex numbers. So you have to consider both phase and polarization. So there'll be complex numbers and there'll be two numbers per point, one for one polarization state, the other one for the other polarization state. So you represent an input as that, and then you measure the corresponding output using the same system, whereby you have a single point for every point in your quantization system on the output, a complex number with two values. And then if you do that, it just becomes a linear system. So every point of the output is just some weighted sum of all of those inputs, because it's a linear system.
Can you explain why the light escapes from one fiber and goes into the others? Normally, fibers are, when isolated, is it because of imperfections, impurities, that light scatters out of one fiber and gets into the others?
Yeah, so in these imaging fiber bundles here, they've designed them for white light imaging. So particularly if you're using kind of green wavelengths, which if you look at a lot of the research on these, they tend to use green wavelengths, then the fibers are far enough apart and have got a big enough refractive index difference to avoid too much light leaking out. However, they're still, to try and maximize resolution, they still have crammed them in. So if you have sort of a 2 meter length, you'll find that you start to be able to visually notice the leaking. So yeah, because you can't perfectly isolate them, so there might be like a small amount of coupling per unit length. But if you have it long enough, that happens. Or if you bend the fiber as well quite significantly, you get variations in the compression causes kind of birefringence, and also a slight sort of shift in the kind of fiber from one bit to the next, which causes light from one fiber to slightly leak out. So that's what you get. So yeah, I use this example here because it's kind of easy to explain. But in a more extreme case, in a multi-mode fiber, if you launch it in a spot, that decouples into loads of different modes in the fiber. So it's more generally speaking, it's more complicated than that. Does that sort of answer your question? Yeah. Yeah. So then, going back to that vector representation again, the output at any given output position is just a dot product of these two vectors, the input and a vector of weights. And because this is not spatially uniform like free space is, because there's random spacing of cores and random bending and random defects, you have to have a different set of weights for every single output position. So this just becomes your output is some matrix times your input, which is exactly links back to this telecommunication stuff I was talking to you about earlier. So it's exactly the same theory there. So the basic idea is that in order to be able to image through these fibers, if we can measure that transmission matrix, we can take some distorted output Y, we can just multiply it by an inverse of that transmission matrix, and we can recover our input vector X. So if the matrix, the way I've represented it here is I've kind of assumed that if you have a square matrix, then it is just one-to-one because you just invert the matrix and there's only a unique inverse. Of course, in reality, like I've sort of shown here, I might scan the fiber across the input. I might scan that across every fiberlet in the input, which may be 1,000 or 10,000 points. But then the output, I've quantized it in a different way. I'm using each pixel as an individual point, so I might have 1 million outputs. So actually, that matrix I measure might be like 10,000 by 1 million, which can't be inverted directly. So in that case, you have to use some other algorithm that applies some constraints, so like a sparsity constraint. For example, in order to get a sort of pseudo-inverse that works correctly. And if you don't do that correctly, you can get garbage out. So the only real way to show that you've done it correctly is to test that it works. But yeah, we need to measure the phase and polarization. I think you will know what this is. Yeah, so in order to do that, we have to use spatial light modulators, which some of you may have used, but for those of you that not used spatial light modulators, they're basically just little screens, and they've got each pixel introduces a phase shift, so it's kind of like a diffraction grating, really. So if you shine like a Gaussian beam on it, say, and you put a particular batten on it, and then you look at the diffracted light in the far field or at the focus of a lens, you get something like that, and then you can actually run an optimization algorithm to customize the phase and polarization in the replay field to be something that you want. So those are kind of a key element of this work. So to build that kind of system that can measure that phase and polarization that we need to do this reconstruction of images, we built this endoscope here. So I won't go through the full optical setup, but the kind of main points that you should note is that right now we have to send light in one end of the fiber and measure it out the other. That's so we can measure that transmission matrix. Also, each optical measurement system is split into two paths. Those represent the two polarizations. And so, for example, we can use the SLM to turn off one polarization and turn on the other one, so we can measure them separately, and we can interfere the two polarizations as well, which is how we measure the full polarization state. And finally, we also use the SLM to measure the phase. And the way we do that is just by displaying some different patterns on the SLM in sequence. So, for example, you can put different focal length lenses on there and measure several different images, and then I can use a phase retrieval algorithm to reconstruct the phase. And you could alternatively have an interferometer straight onto the camera, but I didn't do that in my setup because I basically didn't have a laser that had a long enough coherence length for that to work. So I did that instead, and it seemed to work quite well. So here's an example. So I've sent some letters in to the fiber. This is an imaging fiber bundle. And this was at an infrared wavelength, so 850 nanometers. And at that wavelength, the fibers really leak a lot. So the image comes out quite poorly, as you can see in the middle there. And certainly the phase and polarization are completely randomized by the time they come out. But if we measure that transmission matrix and then we invert it, we can actually recover quite a good quality image on the right there. And depending on your working distance away from the end of the fiber, you can actually get quite significant increase in resolution. So just to sort of explain that a bit more, these are some examples here, and what I've done is I've just, if you take an image right at the end of the fiber, with the fiber butt coupled against something, that's your kind of best raw image, really. If you move away from that, then your image is going to become totally distorted. But if you correctly reconstruct the phase as well, then you can actually computationally refocus the image, and so you can get quite a high-quality image here, even as you move away from the tip of the fiber. So depending on how you define it, actually it does effectively increase the resolution of these optical fiber bundles, which is a useful development in itself. But we also have this polarization information. So here's an example of some, I guess, slightly contrived samples, but that have birefringent properties and also have different dye attenuation properties, and just showing that we can actually image those through the fiber. So we can measure these two useful things. We can computationally refocus, and we can measure polarization properties. But actually, so we kind of developed that, and that was nice, but then we actually realized that phase and polarization in themselves can be used as contrast mechanisms, and there was some microscopy work people done on this. And the idea is that early stage cancer, because it's got a very disordered tissue microstructure, it scatters light more, at least in some cancers, than your more sort of flat kind of healthy tissue you might expect. And also, you often get these dense networks of collagen that form in early stage cancer. And because collagen is a highly anisotropic molecule, you get increased interaction with polarized light. And people have looked at that, for example, when they stretch bits of tissue and they find that the collagen aligns along a particular axis. They can certainly see a difference in the optic axis rotation there. So we sort of decided to test if that was going to work. And so what I was doing at the time is on the road towards eventually testing and clinical instruments, the first step is using tissue phantoms. So we just kind of got these tissue phantoms that were exactly like those things before. They were just contained polarizing structures, and we just stretched them out, and they all aligned along a certain axis, and we were just showing that we can measure a change in the optical retardance there as we stretch the sample. And then to look at the kind of that second effect, which is the scattering of light from phase, we used, again, some tissue phantoms, and we just added titanium dioxide scattering particles and increased that. And we just wanted to see that by looking at the phase maps, we could see an increased scattering, and we do. It's quite a smooth map on the left there, but as we kind of increase the amount of scattering particles, you can see that it becomes more randomized, and we can actually quantify that using an entropy metric to quantify how kind of randomized the phase is. So that's a kind of good first step. But really what we want to do is eventually move towards biological samples. So I was very fortunate to come across some mouse esophageal samples that had small tumors on it that were only about 10 microns in size. And so I was able to take these and image them on several different microscope modalities to try and see the different contrast mechanisms, and then image them with my endoscope and confirm that they matched. So this particular thing outputs a lot of data because you get all of these, these different polarization parameters, the amplitude and the phase. So you get a large number of parameters that come out of this. And so you kind of got to make sense of all those somehow, which was a challenge in itself. So what we decided to do is take a sort of average, and kind of, which basically smooth them. To try and look at some of the parameters like the phase properties and see what that turned up. But then also to look at this entropy, to look at the kind of degree of disorder. And this is kind of, I put the formula there because it's very similar to an average. Instead of just doing a spatial sum, you sort of take an area and you count the number of phase levels in that particular area, and then you just apply this formula. And this was the one that we actually found in the phase image. You can see there produced pretty high contrast for these different features, including tissue folds, but importantly for the lesion features there. So that's the kind of raw image there. But when we tested it over 10 different tumor samples here, we found that when we compared that to the DAPI stained fluorescence images on the top there, we could actually see pretty good features where we expect features, and then for the control samples, we see nice kind of flat samples as expected. So it actually is a pretty good contrast mechanism. So that was a really positive result. But, I guess you might ask, so we've got this transmission matrix now, can we just make a ultra-thin, multimodality, clinically translatable endoscope? Well, I'm sure other people's experience would say that that's a very long way from that. So, what's the first thing we need to do to actually go towards that path? Well, the first main problem is that transmission matrix that we measure, of course, changes every time you breathe, effectively, but certainly when you bend the fiber, it changes very significantly. And so I just did a simple study where I took the same fiber and I bent it 5 times, and I kind of made these into a big matrix, and I sort of basically computed how orthogonal each matrix was to each other, and I got this result here where 1 means that they're perfectly orthogonal. So the matrix basically is completely different when you bend the fiber under any sort of reasonable circumstances. So it definitely needs to be remeasured each time. And that characterization process is a bit slow. People have done it in tens of seconds using digital micromirror devices, but in this particular case, probably the measurements I hadn't really optimized it, but they were taking about half an hour, so that's far too slow. It needs to be improved. So you can kind of overcome this a bit by using special fibers that are designed to be robust to bending. But another thing we found is that even though they change a lot with bending, if I kind of bend the fibers many, many times, and I sort of take an average of the matrix coefficients, you get something that looks like this. So actually, it's not totally random. There is a definite structure there that stays constant. So what you tend to find actually is that it's the phase that randomly varies, and the amplitude of these coefficients tends to stay within certain bounds. So you can use that information to try and speed this up. So that's kind of what we're looking at now to improve that speed a bit more. But probably an even bigger constraint is that people can't really, you need to send light in one end of the fiber, and you need to measure it at the other side. But we want to make an ultra-thin instrument. So somebody is not going to be able to swallow all of that, including spatial light modulators. So really, we need to either miniaturize or eliminate a lot of those distal optics in order for this characterization of fibers process to work. So then, so that's kind of was the challenge that I next started working on to try and solve towards making this a realistic instrument. So my first thought was, well, can we just put a simple mirror at the end of the fiber, and we don't have to have all that stuff? Can we just measure the light reflected back and calculate this transmission matrix? And because you're all optics people, I'm going to go into a little bit more detail here why that won't work, because that's quite important to what we did next. So, I showed you that model of the output times the matrix equals, so input times the matrix equals the output. Well, if you just put a mirror at the end of the fiber, you've got a slightly different scenario. So this is the kind of previous scenario here. But the new scenario is that the input goes down the fiber transformed by that matrix. Then it's reflected off some reflector, which if it's just a mirror, that reflector will just be like an identity matrix, basically. And then, because of you're propagating in the other direction, and optics are reciprocal if you're measuring them in amplitude, phase, and polarization, then you have a transpose of that same thing. So then, really what you're asking then is, can we measure this reflection matrix, which I'm calling C here, and from that can we recover just the forward version A? And I'll just quickly show you without, this part is not critical if you understand the rest of the talk, but I will just go through in case you're interested. I'll just briefly show you why that's not possible. So if we just had a mirror, it's an identity matrix, we just have the product there of 2 matrices, and you can just stick an identity matrix in the middle there, doesn't matter, you can factorize it. But then you can factorize that into 2 matrices that have either +1 or -1 along the diagonal, as long as it's the same in both cases, and those still multiply together to be that identity matrix in the middle. But then you can kind of, separate those 2 things out into, the transpose being times by that and the other matrix being times by that. And I guess the point here is that, this product will still be the same regardless of whether those numbers are plus or minus 1 in the middle. So if you have an n by n matrix, there are 2 to the power of n different possible matrices that could be multiplied by that A and still give you the same product. So if you measure that product, you can't factorize it uniquely. It's exactly the same problem as saying, x squared equals 1, what's x? Could be +1, could be -1, and you need to know that in order to take images. So that's when I got thinking, and I sort of deviated a bit into the world of mathematics. Is there another way? And got me thinking about the second topic that I was working on at the time, which is optical metasurfaces. Don't worry, these will be united at some point, but I'll briefly explain what metasurfaces are. So a metamaterial is basically a material that is engineered to have properties not typically found in nature. So they often exhibit some unusual optical or electromagnetic properties. So here's just some examples. You might have spiral structures that are smaller than the wavelength of light, and they might, for example, take a plane wave and create a circular polarization wave coming out. Or here's something else people often use. They have little structures that are smaller than the wavelength of light, but as a result, they're like antennas, and they sort of resonate together at a particular optical frequency. But then if other molecules become attached to them, they sort of add a certain mass to them, or other optical interactions, they change that resonance. They can be used as sensors as well. And sometimes people even just put samples directly on this, so that the electric field of these kind of nanostructures, evanescent fields, interact directly with the samples. And a metasurface is just a 2D metamaterial. We've only just got one layer. So metasurfaces are often made of sub-wavelength metallic structures. So here are some examples of metallic metasurfaces. And this one here, there's been a structure that's made to create a circularly polarized light. This one here, for example, this pattern here creates a orbital angular momentum wavefront, like a kind of spiral wavefront. And this is some work done by a colleague of mine here, which is potentially of more interest to practical applications, where you can design this particular type of zone plate, like called a photon sieve. But actually, at the nanostructure, you've got two different sort of types of structure that have slightly different spacings between these metal nanodots, and that means they resonate at slightly different optical frequencies. And so at other optical frequencies, they're sort of transparent, but at a particular frequency, they reflect light. So you can use this as a lens, but it only works at two specific wavelengths, and it has a different focal length at each of those. You can kind of tailor things like that, which is quite useful. And this is some of my own work here, just showing that we can make wire grid polarizers using metasurfaces by just making long wires, and we can structure them any way we want to get structures that have all sorts of patterns on them, where you change the polarization and you can see different parts of the pattern. So they can be metallic, but you can also make dielectric structures with something else. So the most common thing you see is these kind of lenses made of these kind of nanopillars, and the thickness of the pillar determines the phase shift, and they're used to make ultra-flat lenses. And this is some work I did with some collaborators in Chicago, in NYU, and this is just showing that you can make holograms instead of just lenses, and then you can do stuff like immerse it in a different refractive index fluid, and you can create different hologram patterns. And you can even combine them together. So this is some work I'm going to be talking about Photonics West, which is when you can combine both. So you can have metal and then insulator metal structures, for example, and that creates a little Fabry-Perot filter there that you can control the wavelength of by adjusting the height. So using grayscale lithography, we can make different height structures that transmit different wavelengths of light. And then, so for example, what we've done in this work here is within the field of a sensor pixel on a CMOS sensor, so a kind of 5 micron size pixel, we've put a whole range of different height cavities, but we've selected the range of heights there such that the overall transmission response is not, instead of just being a bandpass filter, is actually tailored to meet a particular spectral signature that we want to detect. So, and the key thing there is that you can make really small cavities so that you can fit many and make quite complex structures. So that's kind of what they are, and I've sort of doing a little bit of work on that. But how does that help us make these fiber endoscopes I was talking about? So bringing those two things together now, we come to this topic of doing advanced endo-microscopy through optical fibers. So I've already talked about this. It doesn't just work if you put a reflector on the end of the fiber. You've got this ambiguity you can't resolve. But what you can do is you can solve it if you can have 3 different reflectors on the end of the fiber, and you measure all of them, and then that kind of ambiguity is resolved. So how can we generate those 3 different reflectances on the tip of the fiber? Well, and switch between them. So the answer to that is that we come up with is we can switch the wavelength. So the idea is that you have your optical fiber, and you have this structure which has got bits of glass and some optical filters with some metasurfaces sandwiched between them, as shown here. And the idea is that light of different wavelengths will go down, and the first 3 wavelengths you use will totally reflect, be blocked by subsequent filters, and will totally reflect up the fiber. And then you have a final wavelength that goes the whole way through, which you can use for imaging. So those 3 different reflectors there will give you your different wavelengths. And that actually breaks the symmetry. But why do we need the metasurfaces for that? Well, that reflection matrix, in order to be able to be reconstructed, turns out it also needs to be, it can't just be a diagonal matrix. It needs to really mix up the polarizations. The more it mixes them up, the easier it is to solve those 3 equations. So we need a kind of a matrix that takes different modes in the fiber and mixes them all together in terms of space and polarization. So that symmetry is not broken enough using a mirror. So this is why we designed these structures here that have got lots of different polarizing elements that partially transmit light and partially reflect light in various polarization configurations. And as I said, this actually makes it easier to compute the results if it's got more mixing at these structures, because then you can basically isolate them a lot more easily when you're solving the equations. So to show you that this worked, we simulated this using some real measured multimode fiber matrices, and we sort of simulated a setup like this, where we just have the reflector on the end, and we've moved all the optics outside the body now. And so in principle, it is possible to actually do this. But this is a kind of simulation. So what I really want to do is eventually get towards making a device, which many years down the track. But can we actually make these devices that we need to stick on the end of fibers? And this is another thing I'm going to be talking about at Photonics West. So you're all getting a sneak preview here, which is that we think we've got a process by which we can make these. So I'll just kind of briefly go through that. I'm not sure if many of you are familiar with lithography processes, but all we do is we put down some kind of layer of metal, chromium in this case, on a silicon substrate. Then you put down your resist. Then you pattern the resist using electron beam lithography. Then you remove the resist with the developer. So it removes the parts that you've not exposed, or maybe the other way around. I can't remember in this particular case. But anyway, leave some resist there, and then you deposit metal, and that sticks where you want it to. So in this case, we're using gold. And then you remove the remaining resist. But then the kind of key next step that we do is we then use another resist, and we can pattern little discs that are 125 microns, which is coincidentally the same size as a fiber. Then we use an etching step, so we actually then dissolve that chromium layer. We've just got these free-floating discs that have these metallic gold metasurfaces actually encapsulated in them, and here's one there. And so then what we do is we just use an inverted microscope, and we can actually stick these metasurface discs on the tip of fibers. So here's an example of a scanning electron microscope, and we've just stuck a nice little structure there on the end of an optical fiber. And the nice thing about this process is because we're sticking these things, we can easily just keep doing that process, and so we can easily add as many layers as we want, which is eventually where we want to get through for these reflector stacks. And so just as a proof of principle, we decided to try and make some useful structures. So we've just made some wire grid polarizers here. This is what the structure looks like under an SEM. We stuck those on the end of the fiber, and we found that it does have a polarizing. It does do some polarization here. So we just send polarized light at different angles, and the power transmitted is different. The extinction ratio is not as high as we would like, but there's a number of reasons for that. Not the least because we think that the samples are slightly damaged. You can see up there's a few wires missing, which unfortunately does result in quite a bit of loss in performance. But this is kind of the first stepping stone. Once we can make these polarizing structures and reliably make them with good quality wires, then we can easily start making things like zone plates. Very small zone plates that we stick on the end of fibers, and they kind of block light, but they, instead of light kind of expanding out of the fiber, it just focuses to a certain point. So, this is a kind of alternative to sticking a lens on the end of the fiber. But then, the idea of this is that by nano-structuring those rings, we can add things like polarization dependence, or else wavelength dependence too, which is a step further than you can typically go with conventional optics. So I guess the kind of vision here is that these metasurfaces will help achieve these next generation endoscopes. So one design is this multi-layer stack structure, which will allow us to do phase, polarization, and things like confocal imaging, which is where I started out. Going on to this other work that's talking about Photonics West, by using these metal insulator metal structures, we can do things like multispectral imaging. We should be able to add spatially varying multispectral filters that are customized on the tips of fibers. But I think thinking more broadly, and this is where some projects that I'm working on with people here, is to look at a wide array of other structures, such as Fresnel zone plates and things like that with nanostructures. And again, these can be tailored to other modalities. So the idea is that for all these different modalities, we're going to try and find structures on the end that we hope can enhance them or offer improvements in some way, with the ultimate goal, like I mentioned before, of having this structure where we can just pipe those microscopes to the tip of a fiber, ultimately with the goal of being able to then insert those fibers into needles or other very, very thin imaging instruments to use in pancreatic and ovarian cancer. So that's kind of where the technical work is. It's quite early stage from a sort of clinical instrument point of view. So in parallel, we're trying to do a few other things to get towards clinical translation. So the first thing is we need to improve these fabrication processes. So for designing metasurfaces, it's very important that your simulations match what you can fabricate in the clean room. That's because fabricating in the clean room takes a very long time, and it takes a long time to iterate through different designs and different metals and so on and so forth. So if you're confident that you can simulate what you can fabricate, then you can try a lot of designs much more quickly in simulation software. And as I said, the polarizers don't work that well, but a lot of them have various defects like that. So we need to try and just be able to identify those and remove those ones. And sometimes when you glue them onto the fiber, there's kind of unevennesses in the surface. So there's things like that we need to iron out to get these to be a bit more reliable. And we also kind of need to figure out what our kind of minimum viable product is to prove this technology. The second thing we're working on is that, as I said, this is a bit slow, so that the measurements required to do a transmission matrix is quite slow, but I briefly alluded to the fact that the matrices are actually highly structured. So there is a lot of prior information that could be exploited, but it's a bit difficult to figure out how to do that mathematically. So a way that people are turning to a bit more now is to use artificial intelligence techniques to automatically learn that structure. And they're using things like convolutional neural networks. So people have shown that convolutional neural networks can learn those fiber transmission matrices and be used to reconstruct images. Based on real data sets. And so, this is just for the forward version where you're imaging through, but we're trying to apply this to do the this transmission mode thing, which actually turns out to be a harder problem. I think, it actually seems to be harder, but we're having some progress there in being able to replace our current reconstruction algorithm with a deep learning model, which we hope will in the future allow this to be a bit quicker. So the third thing we're doing is, as a sort of quicker way to try and validate some of these things before we stick them in animals or in people, is to try and use tissue phantoms. So I sort of briefly mentioned this, but the idea here is to try and create physically realistic samples with realistic tissue properties. So this is my PhD student is making these samples, and they're kind of a polymer that has titanium dioxide and also nigrosin dye, so we can control the absorption and scattering properties to match. So this is one which is trying to simulate a tumor with different properties, and we can extract the height and also the absorption and scattering properties. So they're made from mineral oil base, and then we use agents to make the scattering and absorption like realistic tissue. And you can look up these properties for different types of cancers and what they are. As a sort of side project during the pandemic when the labs got shut down, we realized that you can actually do pretty good ray tracing simulations of scattering and absorption properties just in Blender, which is a free 3D rendering software that actually does pretty good simulations of light scattering inside materials and absorption. And so we sort of, as a nice pandemic project, we managed to make a simulation that could simulate this whole process. And that also then, like I mentioned, for the other simulations, allows you to test out different geometries, like this one here, for example, which is more of a luminal geometry, which is what you would kind of expect in a clinical environment. So we're hoping that this could be a sort of test bed for testing. This is kind of spatial frequency domain imaging, which I don't really talk about very much, but just for testing spatial frequency domain imaging and different types of illumination patterns and seeing which ones produce good results very quickly. Yeah, so I think, taking chemicals together, what does the future hold? Well, I'd like to see practical and useful meta-optics designs stuck on the end of fibers. So practical and useful means things we can make and that actually work, and then also that clinicians need. So I need to sort of bring those two aspects together to make sure that they're going to work. So the idea is to try and have a range of designs that work for different modalities and to test them, starting on phantoms and then on ex vivo samples and eventually in clinical testing. But I think the use of AI is going to be important for improving the reconstruction and dealing with things like noise. I think there's also various other projects that I'm working on that might be related. Different types of fibers, for example, is another thing that people are exploring a lot. And I'm also doing some work on hollow core fibers, which you can send modes down as well. And they've got their own interesting properties that can be very useful for certain wavelengths of light, for example, that don't propagate in glass. Or if you want to sort of, do optical biopsies, you can actually get tissue kind of slightly inside the fiber. So I think there's a lot of kind of interesting directions this could go in. Yeah, so to finish off, just if you're interested in this work and you like what you see, then you're always welcome to come and visit me or drop me a line. And I'm always open for discussions and collaborations. I really like working with other people and sharing ideas. So with that, I'd just like to thank everybody, including my collaborators here, Jennifer and Travis. And I'm open to any questions now. So, hi.
Yeah. So if you took this, say, single mode fiber and put gold coating or some other metal coating on the outside of the cladding, let's say 100 nanometer coating of gold would be enough to make it totally opaque. And then if you bundle these fibers together, then the light will not escape from one fiber to the next. And it will still be flexible. Why can't something like that work to prevent this leaking among the fibers?
Yeah, that's a good point. So when they make these multi-core fibers, they make like a sort of like a preform first, and they take like thousands of kind of rods of silica and they kind of put them together. So what you would do in that case is, well, you probably put a thicker layer of gold because when it's extruded out, you need it to extrude out to end up being 100 nanometers. If you want to have that high density of fiber cores. So I guess what I don't know there is how well does the gold extrude compared to the glass. If you draw out a metal inside the glass, does it kind of extrude at the same rate? Yeah, so that kind of, you'd have to ask a fiber fabricationist about, yeah.
To extrude them together because the melting points of silica and gold and aluminum are not the same. But all I'm thinking is that, make the fibers the regular way and then put them in an evaporating machine. You don't have very long fibers, there's a few meters, I suppose. Just evaporatively coat 100 angstrom, 100 nanometer of gold on them. And if they're flexible enough, then you can just bundle them together afterwards.
Yeah, so I guess if you could make, so the fiber bundles I show you, they're actually like a solid piece of glass, right, with just the kind of cores, effectively, just refractive index. But I guess maybe you could, if you could make like 2 micron width fibers by themselves, you could do exactly that, which might be interesting. Yeah, I've never worked with fibers that thin before. I don't know what they're like to work with. I wouldn't want to drop one on the ground; you'd never find it again. But but that might be possible. I don't know. I'd be interested if anyone else knows more about that than me.
Maybe you can clarify something about these metasurfaces. So what you're trying to do is, maybe I misunderstood you. You just want to make a mirror that's reflected at 3 different wavelengths. Why not just use a dielectric stamp? sort of a format?
Yeah. So, I mean, effectively, those kind of filters that I'm using there, that they would probably internally be that. So the only difference, but I want like different. I would need like several different stacks just because I want one to reflect one wavelength and want it to transmit another wavelength. So the reason you can't just do that is because in order to be able to get the information you need to do that, solve those equations, you have to mix the polarizations up. So what I mean by that is, if you just have like that structure, polarization reflected will just remain the same. But what I need is like polarization that goes in to come back to be some other state of polarization, and I need that state of polarization. I need that to be different across the whole surface. So if I send like a vertically polarized light, I might want here to come back horizontally. I want here to come back elliptical state. So that's why. So it basically is exactly what you said, except I've just cut the stack up and stuck some metasurfaces in at the appropriate point. But there may be, it may be that once we refine the design, we might be able to just do something clever, like just have the metasurface in the middle and not have to have all those layers separately, and just have a dielectric stack. There might be something like that we could do.
So which means there will be lots of noise in the images. So how do you mitigate or analyze these noises?
Yeah, so some of the noise in this will come from as the fiber bends, it distorts the image slightly. So the goal would have to be to try and take the characterization measurements you need as quickly as possible and as close to when you want to take the actual image as you possibly can. Then that would minimize the noise from that source. And also, of course, biological tissue has got blood flowing through it, and people are moving, so that's also another source of noise. So the actual time at which you're taking the image would have to be short enough that it's not affected by that. And the difficulty there is often with the amount collecting enough light, because the fiber is very small and doesn't have a big aperture. So, but I guess hopefully you could argue that if you can have the optics outside the body, then perhaps you could afford to have a slightly better camera that's cooled or something, and and so it can work with lower levels of light. Maybe that would be part of the argument for this kind of design. I think we had over there. Yeah.
So how much does this transmission or this A matrix change on small distances? Like you have a fiber core and then you have some space in between another fiber core. Does it change just when you scan the dot above these different fibers? Does it change dramatically from one fiber to the next one? If it's in between, so it's a function that is really, really dynamic, or is it more or less the same at one location in your?
It's a bit like there definitely is some correlation, but it's a bit like a speckle pattern. If you kind of average them all together, they all have a kind of nice kind of smooth shape, but each individual one has got random speckle, and if you move it to the next fiber, the pattern will move, but it will have a new random speckle. So not very correlated. It is in terms of this sort of envelope. It's always a kind of Gaussian shape, but the actual detailed structure of it, the speckle pattern, is pretty decorrelated from fiber to fiber.
But when you scan the matrix, you're not trying to get the dot or the input directly on the core. You just scan it along a line, and you take whatever comes back. That's what you measure.
So I scan it along. Yeah, you're right. And I don't put it on the fibers. That has a couple of advantages. One is that with these multi-core fibers, actually you can slightly image in the space between the cores, which is one of the ways you can overcome that. The light is a bit leaky; it's pretty lossy in there, but you can still use that. So that's one reason. The other reason is that to focus light on an individual core, you have to have a super high numerical aperture, and that means I can't scan like across a large area. There's a decoupling there because I could put as many fibers as I want together. How am I going to scan a 4-micron spot across a millimeter? That's quite a big ask without significant aberration. So I tend to use a slightly larger spot that covers many cores and then just scan it in small steps, if that makes sense. I think you were... Oh, who was next? Okay. Yeah. Yeah.
So what is you showed a picture in the beginning of the talk, near the beginning of the talk, of a fairly large field of cancer there and some cancer. What is the field of view that you would get from this 100 micron or 100 micron size endoscope? And how would you actually image something that looked like that?
Yeah. So that's a good question. That's a kind of big thing that we talk about a lot. So the field of view for like an optical fiber with no lenses on the end or anything is just the numerical aperture. So that tends to be, you can buy multi-mode fibers with very high numerical aperture, but the kind of those core fibers really, they're not that high numerical aperture. So you're sort of looking at a sort of well, I couldn't tell you exactly what it is, but it's not like it's definitely nowhere near like 180 degrees. So what you yes. So and the sort of field of view then, it's not quite like a lens because you're sort of refocusing it. So it's like kind of like more like a telecentric type thing, right? So I can image in any plane in that kind of cone, but with the same number of pixels. So the area that I'm seeing is proportional to the distance away from the fiber, but then the resolution per pixel is also less. So the idea is that you could sort of look at a distance away. In reality, I would, if I want to get a high field of view, I'd just put some sort of lens on the end. Or if you're doing computational stuff, you can even just put a scattering surface on the end to get a high numerical aperture. I guess the advantage of the lensless stuff is that because you can computationally refocus if you're measuring the phase, then you can, in theory, do depth sectioning from that, so you can look both up close for like an optical biopsy, which is when you'd want to look at the sort of cellular level, and also you can focus further away if you sort of spin your endoscope round, so you're kind of looking down a lumen. Does that make sense? Yeah.
I guess your general approach of figuring out A matrix and then inversing the problem can be also applied to just a single core multi-mode fiber, I guess, right? So between fiber bundle, like multi-core fiber bundle versus single core multi-mode fiber, do you see any sort of advantage of using one over the other? So I guess with fiber bundle, your information is still confined to more or less kind of that area. So maybe it might be more or less susceptible towards bending or things like that. But so, do you have any comments about it?
Yeah. So people like the multi-mode fibers, I guess, is people. The thing they like about that is that I think, in principle, if you use all the modes, because they're orthogonal modes and they're all on top of one another, you can kind of get more maximize your resolution per unit area. So you can get, 100 micron core fiber has got 100,000 modes maybe. Therefore, you could do like 100,000 pixels of resolution, but only in a 100 micron area, which is much better than a fiber bundle, which will be a millimeter size to get that number. So in principle, that's the nice thing. The reason I used multi-core fibers is because there's still this issue for surgeons, particularly like navigating. So they want to see where they are and want to do it instantly in real time. And you can do that a little bit because the images are a bit distorted, but they're still usable. So you can kind of have a kind of low res mode when you're just looking at the raw data moving around, but then you can like flick on your matrix recovery and get a higher resolution. So that's why. And in terms of bending, again, you still always get that imaging. The multi-mode fiber is much more destroyed. You can still get that rough image from a multi-core fiber when it's bending. But there are designs of fibers that are much more robust to bending. So there are multi-core fibers where they twist them, and that actually is much more robust to bending because you've kind of got the spiral, and if you bend it, the kind of spiral covers the whole bend. So there are designs that are more robust to bending, but they tend to be of the multi-core design rather than the multi-mode design. So that might be a direction to head in the future. Good. No more questions? Guess I'm off the hook then.
Thank our speakers.
Thanks very much.